Hi, I'm Carl Hose, and I'd like to welcome you to ARC Magazine MasterClass. Today we're going to be talking about welding on Inconel 625. Inconel is a trade name for one of the many nickel alloys that you can encounter while welding. There are many families of nickel alloys, but Inconel is one that's popped up lately in motorsports applications, primarily high-end exhaust systems. Inconel 625 is considered a non-ferrous material. Basically what that means it is nickel-based and not iron-based. Ferrous materials like carbon steel, stainless steel, those are iron-based materials. Inconel 625 typically contains a nominal 60% nickel, 21% chrome, 9% moly, and can have small amounts of iron and niobium and other elements in it. Primarily the reason it's used for exhausts on motorcycles, it's a solid solution alloy, and it works very well at intermediate temperatures, intermediate to high temperatures used for exhaust systems in motorsports. It allows them to use a thinner wall thickness than they would with a stainless steel exhaust system, a similar exhaust system made out of stainless steel. I have a couple parts here. This is a used collector for probably an Indy racing team, and you can see that this part has been operated at high temperatures. It has a dark oxide coating on the surface. The oxide's been sanded off. This is probably operated at 1800 degrees to get that oxide coating. When the Inconel is new, the tubes that are manufactured by the header manufacturers, custom header manufacturers, they generally make their own tubes, and it's made from sheet. And often these parts are polished to a chrome-like finish. They're very expensive headers, so they're polished to a chrome-like finish. They start out with sheet, and the sheet sometimes has some numbers on there. In this case, you see there's an aerospace material specification here, and there's also the 625 for the nickel alloy we're working with. These parts can quite often be quite thin. The idea of using them, and the reason they're paying the extra money for this expensive material, is that they can cut the wall thickness in half. Headers can be as thin as 19 thousandths, 28 thousandths is pretty common, and even 35 thousandths. The part I'm welding today is going to be 28 thousandths thick. Nickel alloys are used in many industries. It's used in chemical processing because of their extreme corrosion resistance in various corrosive environments. It's used in marine applications for its corrosion resistance in salt, chloride ion, stress corrosion cracking. It's used as a cladding material sometimes for corrosion resistance, and paper mills, nuclear industry, on and on. There are many applications for nickel alloys. The rules for welding them are similar whether we're using it for a motorsports application or for other industries. The Inconel 625 we're welding on today is exhaust parts, and a lot of these parts are formed and bent into U's and different degreed angles, and when they deep form them, they use lubricants. It's very important before we weld on this material to remove all the lubricants, any kind of Sharpie marks, anything that's not proven to be safe at high temperatures with nickel alloys should be removed with a safe cleaner. The Inconel that I'm going to be welding on today is about 28 thousandths thick, which is pretty thin. And I've got the parts cleaned up and tacked already, so I will be welding them at about, the rule of thumb in TIG welding is 1 amp per thousandths of an inch of material thickness, but because this is nickel alloy and very similar to stainless as far as thermal conductivity, it does not conduct heat very well, so I'm going to run probably about 20% below the amp per thousandths rule. That's just kind of a rule of thumb. I'll probably be down around 20 amps, maybe a little lower because these parts have been stretched thin. So I'll be running a purge. I'm running an Argon Purge on the inside. I've taped up the ends with a safe tape. It's a painter's tape that doesn't put glue on the pipes. And I'm running 15 cubic feet per hour flow rate. I'll be welding today with a Techalloy 625 045 solid filler wire. That's available in cut lengths and in MIG wire as well, in all the way down to 035 diameter wire. With small, thin tubing like this, you need a small wire. So 35, 45 wire is typically what we would use for filler on this, if we use filler at all in this application. I'm going to be using a Magnum PTA 17 torch with a flex head that comes standard with the Precision TIG 200 square wave. I'm also added a different type of gas lens on here. I'm using a large jumbo gas lens with a number 12 cup. The inside opening on the number 12 cup is 3/4 of an inch. Using the bigger cup to cover a little bit longer as the material cools, to keep the oxidation off primarily. The material is going to cool slow because it's very thin and has poor thermal conductivity. I'm running a flow rate of 30 cubic feet per hour on the primary gas, and I'm running 15 cubic feet per hour on the purge on the inside. Okay, we're going to talk about separating these materials. Sometimes we get a lot of parts donated from header shops, and we will get some stainless and we'll get some Inconel. They come in the same box. We weld on these in our advanced motorsports program. Very easy to get them mixed up. Also, sometimes a mechanic will bring us a header at the racetrack to weld on, and I'm not sure whether it's a 321 stainless or an Inconel. Little trick that I've learned over the years is stainless steel, when you cold work it, it work hardens and becomes magnetic. So this is a piece of stainless. I can tell because of the magnetism. Also, any seams that are on this, if there's a seam in the weld will also be slightly magnetic. When we work with Inconel 625s, even though nickel itself is a magnetic material, these nickel alloys are totally non-magnetic. The welded seam on the tube is not magnetic, and after it's been cold worked, it does not form into a magnetic structure. So I kind of use that as a way of guessing as to what material this is. If I can't figure that out that way, I weld with Inconel filler metal. 625 filler metal is what I would use to weld even stainless. It would work. If I had to join dissimilars like stainless steel to Inconel, I would use 625 Inconel filler metal. Okay, we're going to get started welding. I'm going to turn on this square wave TIG 200. And we are set for direct current TIG welding, negative polarity. I have the current turned way down to 19. I'm going to bump it up just a little bit. I'm going to shoot for 22. 28 thousandths material, take 10% or 20% off of that, you're down around 22. Depending on the thickness of the materials, how it was stretched and formed and everything, we might back off that foot pedal a little as I weld. I have a 1/16 thoriated tungsten in here. We'll see how we fire up on this little piece. Argon flowing 30 to the torch. I got 15 right now running inside with some holes popped in the end to let a little air out of there. You see a little bit of a green arc to Inconel that you don't see with stainless, and it's a little sluggish on the surface. When I started out, I set my top current at 22 amps, but I can tell welding on this piece that it's a little thinner than 28,000, so I'm back that current down. I bet I'm down around 17 amps or so right now. Fit up is very critical. If you have a gap on material this thin, you're going to have a real hard time filling that up. Trying to keep my work angle torched pretty much straight in. Filler wire added to the front if I'm using filler metal, which I am today. And travel speed just enough to let that puddle wet out. You got to kind of take your time with these nickels. Again, we're not worried about getting to the inside. 28 thousandths material, it's going to break down on the inside very easily. What I try not to do is make the weld too flat on the surface. That's why I'm using filler. Okay, I'm coming around here and getting up near the end of the weld. What I want to make sure I do is to fill the crater at the end. So I'll bit off the pedal real slow, give it a little extra filler metal there, and keep the torch right on the puddle. Keep the gas flowing over the crater until it cools down. We keep the argon on there to protect it. Any oxidation that's on the surface, if discoloration, it needs to be removed. It needs to be removed with a clean stainless steel wire brush. It hasn't been used on other materials, or polishing cloth, emery cloth, anything like that can be used to buff the welds down. But make sure it's clean. It hasn't been used on other materials. You don't want to embed iron or from other operations into the surface of the nickel alloy. Thanks again for watching ARC Magazine Masterclass.